Welcome back, everyone. If you are fascinated by how AI is fundamentally reshaping software development, you are in exactly the right place. Today, we've got some massive AI news to cover. For this explainer, Cohere just dropped North Mini Code, and it's their very first model built from the ground up specifically for developers. Now, this isn't just another autocomplete plugin. No, it's purpose-built for real agentic software engineering tasks. So, let's lift the hood and see exactly what makes it tick. Here is the roadmap for our explainer today. First, we'll meet North Mini Code. Second, we'll cover the Mo architecture. Third, training for agentic excellence. Fourth, robustness across developer tools. And fifth, deploying and sandboxing safely. All right, Section 1, meet North Mini Code. From autocomplete to autonomy. Let's kick things off with a standout metric, 33.4. That right there is North Mini Code's score on the Artificial Analysis Coding Index. To put that into perspective for you, it means this model absolutely outperforms significantly larger models like QWN3535B and Gemma 426B. It even holds its own against absolute behemoths like Nimtron 3 Super and Mistral Small 4, which are packing over 100 billion parameters. So for its size class, it is without a doubt one of the strongest open-source coding models out there. And that incredible score, it's driven by a profound shift in philosophy. You see, standard LLMs prioritize static completion and syntax correctness. Basically, they just finish your lines. But North Mini Code is entirely optimized for autonomous execution and multi-step tool interaction. It's actually built to interact with your terminal, maintain persistent shell sessions, sequentially execute commands, and then react to the outputs, all without dropping context. It's a real game changer. Okay, so let's look at the baseline specs enabling all of this. We're looking at a 30 billion total parameter model, but here's the kicker. It only uses 3 billion active parameters per token. It's running on a decoder-only transformer backbone. Plus, this is a massive win for the developer community. It's released under the permissive Apache 2.0 license. The weights are sitting on Hugging Face right now in both BF16 and quantized FP8. That means you are totally empowered to self-host, fine-tune, and integrate it with zero restrictive licensing headaches. Moving on to Section 2, the MOE architecture explained, or efficiency at scale. So the secret sauce here is that North Mini Code utilizes a sparse mixture of experts, or MOE architecture. Just to make sure we're all on the same page, MOE is an architecture that uses specialized subnetworks. Instead of firing up the entire massive neural network for every single word or token, it selectively activates just a few. It's brilliant because it saves a ton of compute while maintaining an incredibly high capacity for complex reasoning. Under the hood, this model packs an impressive 128 experts in its feed-forward blocks. But get this, only 8 of those experts are activated per token. By routing the data to just 8 out of 128 experts via Swidgeloo activation, latency drops drastically. And when you've got an agent iterating through long debugging loops or running extensive test suites, cutting down that latency is absolutely critical for real-world performance. Furthermore, the attention configuration is heavily optimized. It uses a fascinating 3-to-1 interleaved attention ratio. That's 3 layers of sliding window attention with rotary positional embeddings, which is what helps the model track the exact sequence of your commands, followed by 1 layer of global attention without any positional embeddings. Why does that matter? Because this specific split lets the model preserve those vital long-range dependencies, like your terminal history from 10 minutes ago, while still managing the immediate short-term context super efficiently. Which brings us to Section 3, Training for Agentic Excellence, Building an Autonomous Agent. You can't just feed raw code data to a model and expect it to magically become an agent. Cohere used a really strict 3-phase post-training pipeline here. First up, Stage 1 Supervised Fine-Tuning, or SFT. Then, a highly filtered Stage 2 SFT. And finally, an intense reinforcement learning phase called RLVR, that's reinforcement learning with verifiable rewards. The really cool part is that they didn't even optimize for benchmark metrics during SFT. They strictly used those SFT stages as a primer for the final reinforcement learning phase. Let's look at the Stage 1 data mix. It is heavily weighted toward tool use and reasoning. We're talking 43% agentic tool use, 30% reasoning and instructions, and only 27% standard single-turn programming. They literally forced this model to learn how to call external APIs, parse JSON, and chain commands together from the jump, rather than just spitting out isolated functions. Then they use this brilliant concept called the long-to-longer cascade. In Stage 1, the model trains with a 64K context window. But in stage 2, that explodes to a 128K context window, using 4.5 billion tokens of only the absolute highest quality, verifiable agentic samples. Splitting it up this way prevents behavioral conflicts. If they had mixed it all together, the shorter, non-code data from early training would have drowned out the high-quality long-context data, and performance would have tanked. Now let's talk about that final phase, reinforcement learning. Training an agent is messy. One debugging task takes 10 steps, the next takes 100. In a normal, synchronous learning loop, the trainer just sits there twiddling its thumbs, waiting for the long tasks to finish. So Cohere totally decoupled sampling from training with asynchronous RL. They used a windowed FIFO queue to handle those long straggler rollouts in the background without stalling the trainer. Plus, they aggregated the loss at the token level, meaning long, complex agent traces don't get unfairly penalized. And the results of this RLVR phase, honestly, they are stunning. The SFT-only model was already great, hitting an 80.2% pass rate on SWE bench. But after RLVR, during human evaluation, the model achieved a massive 66.1% win rate boost, specifically on code editing tasks. It also grabbed a 7.9% absolute boost on terminal bench v2 simply by reducing invalid and hallucinated tool calls. Basically, it learns to stop endlessly looping and actually submit the working solution. Section 4, Robustness across developer tools, ready for the real world. It's easy to win on paper, but how does it handle the real world? Well, Cohere evaluated North Minicode across multiple real-world harnesses developers use every day, testing over 70,000 verifiable tasks. You've got SWE Agent with its bash and edit tools, MiniSuite Agent providing raw, messy shell stayout output feedback, OpenCode requiring fine-grained JSON parsing, and Terminal Bench using plain text chat. This model handles the whole shebang, from perfectly structured JSON to chaotic shell outputs. I want to highlight a really fascinating quote directly from their research. Cross-harness transfer can be cheaply acquired without degrading benchmark performance. Essentially, by adding just 6% of additional benchmark data during that second SFT stage, they triggered massive gains, like a 10% boost on OpenCode, without losing performance anywhere else. It proves that the skills needed across different developer environments are actually complementary, not contradictory. Let's get into Section 5, Deploying and Sandboxing Safely, Implementing North Minicode. So how do you actually run this thing on your own hardware? First, your inference backend must support MOE routing and the specific attention setup. Frameworks like VLLM, TGI, or Cohere Native are your best friends here. And a quick reality check on the hardware. Yes, it only uses 3 billion active parameters per token, which makes it lightning fast. But you absolutely still need enough VRAM to load all 30 billion parameters of those expert weights into memory right at the start. Now, I need to take a serious tone for a second. Safety is absolutely paramount here. Remember, this is not a text generator. This is an autonomous agent designed to have terminal and file system access. It can literally execute arbitrary commands. Sandboxing is non-negotiable. You must deploy it inside isolated containers, strictly restrict its network access, and use read-only base file systems wherever possible. Do not, under any circumstances, give this model unmitigated access to your production environment. Finally, Section 6. Conclusion: the agentic workforce. North Minicode, powered by its highly specialized MOE architecture and that incredibly rigorous RLVR training pipeline, represents a massive leap forward for open-source AI tooling. We are officially crossing the threshold. We're moving from passive tools that just finish our sentences to active agents capable of autonomous action. The capabilities are here, and amazingly, they're open source. So it leaves us with one critical question. As models move from autocomplete to autonomous action, is your infrastructure and your security architecture truly ready for an agentic workforce? Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll see you in the next one.